This video is to demonstrate the use of the Carbon Storm carbon accounting tool for urban and developing landscapes. This tool was developed to provide a calculation of the carbon footprint for both at a planning scale, such as might be associated with any sort of urban development and the types of impervious or pervious surfaces used, but it can also allow users to zoom into the finer design scale details of individual landscape elements, particularly such as different types of stormwater control measures. Just to give an example of different types of applications, at the planning scale, one might be interested in trying to reduce the carbon footprint of, say, a conventional approach to development with an approach that incorporates more natural vegetation and soils on the site. So that would be one way that the model could be used. At the higher, finer scale design details, some applications of that could include comparing carbon footprints for different types of stormwater controls and then using that as a type of stormwater control measure selection that also factors in the carbon footprint of those practices, or even getting into the design and construction and maintenance details of individual practices and thinking about how factors such as the types and extent of vegetation, the locations from which materials are sourced, or even maintenance regimes impact the carbon footprint, and using that information to fine-tune your design and maintenance plans to minimize the carbon footprint associated with those elements. Regardless of the application, though, the Carbon Storm follows life cycle assessment and carbon accounting methods that have been outlined by the International Organization for Standardization. And those include accounting for the entire life cycle of the landscape and its individual components. This would include the carbon that's embodied in the materials used in construction and then later in maintenance, including the carbon used to extract those materials, transport them to the production facilities, and then manufacture those materials as is appropriate to the particular material. In the next life cycle phase of these landscape elements, we consider the construction emissions, which would be both fuel used by equipment during construction as well as that consumed in transporting equipment and materials to the site. During the maintenance phase of the landscape's life cycle, the model considers emissions that are accumulated through the transport of both equipment and crews to the site to maintain the different surfaces and landscape elements, as well, again, as any of the energy that's embodied in the materials used in maintenance and fuel consumed by types of maintenance equipment. For those landscape elements that includes vegetation, the model also considers potential for carbon sequestration over the design scale or lifetime expected for that particular practice. So then to calculate the carbon footprint, the model simply sums the embodied carbon and construction emissions, and then the maintenance and sequestration rates over the time frame of interest, which again is typically taken as the expected design life for that stormwater practice or urban surface, etc. So next, I'll demonstrate the model interface and how one can use this model to answer questions or show the carbon story for a particular type of development. Once logged into the model, users of the Carbon Storm model can select from any number of different types of landscape components and then use these to build a representation of your site and its various stormwater control measures or pervious and impervious coverings. You can see that the model includes several common types of stormwater control measures, which is as well as conveyances, which is a unique aspect of this model compared to other carbon accounting tools currently available. For this example, I'll demonstrate a planning scale application where we might be interested in looking at the reduction in the carbon footprint we can achieve by adopting a more carbon-friendly approach, we'll call it, where we've incorporated more natural vegetation and maybe even some existing drainage infrastructure on the site. To compare this, though, we need to first look at what a conventional development might look like. And so for that, we'll take some standard pavements, and we'll consider that our parking lot in this example. Our site might also be expected to have at least some landscaped area, and so we'll call this our landscaping, and we'll come back and specify that further. But first, we will take a look at the parking lot, and in doing this, have a look at the various parameters that can be specified within this model. So for the pavement type, we have a choice of different types. I will select the asphalt. And for this example, I'm just going to leave in many of the default values, but we'll say that we've got about a hectare worth of paved area, or just under 25 acres. On the design side, if this is where if one was choosing to try to optimize some of those design parameters, you could look at different ways of designing the site and its landscape components. After the design parameters are specified, the next two components deal with the construction and transport and site preparation. I'm going to leave in the default values here, but one can specify the distance for both your construction materials as well as the equipment being used at the site, the types of equipment being used to prepare and then construct that parking lot in our example here. And then finally, a maintenance phase of the life cycle where you can consider street sweeping or other routine maintenance activities that would be occurring at this parking lot that we have in our example. Because we don't anticipate vegetation in our system, there is no sequestration component for this parking lot's carbon life cycle. So I'll save those edits. For the landscaped area, now we have a choice of the types of vegetation we want to have in our parking lot. Again, this is our conventional example. So I'll just enter in some values. We'll say we're using, we'll go with half a hectare total of grass. We'll leave our maintenance period to be 20 years, thinking that might be a design life for this site. And then we'll maintain about 200 trees and another 100 shrubs in this example. Similar to our parking lot materials, we then have a construction life cycle phase, which is going to deal with the transport primarily of those our trees and our sod to our site. And then the maintenance would be any of the mowing, irrigation, if we would be irrigating or fertilizing the grass and trees, as well as a pruning factor. So again, the default examples can be accepted, or one can specify those out a little bit further. For this example, we'll say we're going 100% irrigated, and we'll just go with that. Once the site or the modeled landscape is representative of what you are trying to model, you can name it. We'll call this our conventional lots, and we'll create the new run. Here we now have the results of our carbon footprint, which breaks down those various life cycle phases into the embodied carbon, construction carbon, maintenance carbon, and then finally the carbon that would be sequestered through the vegetation in our site. And so the sum of all of these components for our example here is just over 81 tons of carbon. If we then wanted to look at opportunities to reduce this by perhaps adding more vegetation, maybe doing some adjustments in terms of the amount of impervious surfaces that we need, you could just directly edit this run. I'm also going to edit it by switching out some of the standard pavement for some permeable pavements. Okay. And we can go in and make some reductions. So for our example, we'll just assume that we're going to be able to reduce our overall impervious area by about 20%. So I'm going to reduce here and then add in some permeable pavement. Again, that's all I'm doing for this reduced carbon site. Oops, let's see. Let's say that's 3. Edit our existing pavements. And then for our landscaping, as we've been able to decrease some of the impervious area, we could envision being able to increase the amount of turf that we might have on site. So we'll go up to, we'll add another couple thousand here. And also increase the number of trees and shrubs we have. And then we'll accept this. And in order to keep track of these, we can give this a different name. We'll call this our vegetated lot. And creating our new run. Once again, we can see that our materials and construction and maintenance emissions are reported, our sequestered amount as well, which has increased because of the additional trees in our lot. But here we've actually increased our total carbon because of some of the additional materials required for the permeable pavement. And so we would want to probably go back and make some further adjustments there. But that is an example of how this model can be used to get your site's carbon footprint.